So in CP's theory, Khosla theory and concept of flow net is completed. So the seeping water which does not creep along the bottom contour of Pakka floor as a straightwise leak. So in other hand, this water moves along a set of a streamline and this steady seepage in vertical plane for a homogeneous soil can be expressed by Laplace equation. So that is also discussed. So in Laplace equation, which represents set of curves which intersect to each other orthogonally. So what is Laplace equation? Laplace equation is del square phi by del x square plus del square phi by del z square equal to 0, where phi equal to flow potential and flow potential equal to kh. So where k is the coefficient of permeability of soil, which is defined by Darcy law, and H is the residual heat at any point within the soil. On the set of line is called a streamline, and the other set is called equipotential line. So the streamline represents the path along which the water flow through the subsoil, and every particle entering the soil at a given point upstream of the structure will trace out its own path and it will represent a streamline. So the first streamline follow the bottom contour of the structure and is the same as per oblique path of creep. So the remaining streamline follows smooth curve which transiting slowly from the outline of the formation. Streamline and equipotential line. So equipotential that is treating the downstream bed as datum and assuming no water on the downstream side. So it can be easily stated that every streamline possesses a head equal to h1 while entering the soil, and when it emerges at the downstream end into atmosphere, its head is 0. Thus the head H1 is entirely lost during the passage of water along the streamline. So further at every intermediate point in its path, there is a certain residual head H that is still to dissipate in the remaining length to be transverse to the downstream, and this is fact is applicable to every streamline, and hence there will be point on different streamline having the same value of the residual head. So if such a point are joined together, the curve obtained is called equipotential line. So we can also see by diagram, this is the any hydraulic structure. Here is the head and here is the no head. So flow is this way. This is the this vertical line is equipotential line and this path is streamline. This is the flow net. Difference head difference is h. Here h. Here is the small h. Okay. So the seepage water exerts a force at each point in the direction of flow and the tangential to the streamline. So this force has an upward component also from the point where the streamline turn upward, and for soil grain to remain stable, the upward component of this force is counterbalanced by submerged weight of the soil grain. So this force has maximum disturbing tendency at the exiting, and because the direction of this force at the exit point is vertically upward, and hence full force acts as its upward component. So for the soil grain to remain stable, the submerged weight of the soil grain should be more than this upward disturbing force. So the disturbing force at any point is proportional to the gradient of the pressure of the water at that point, that is the dp by dl, and this gradient of pressure of water at the exit end is called the exit gradient. In order that the soil particle as exit remain stable and the upward pressure at exit should be safe. In other words, we can also say the exit gradient should be safe. So for safety purpose, safe exit gradient and critical exit gradient we have to study. So generally exit gradient is equal to 1 by 4 to 1 by 5 of the critical exit gradient. For different types of soil, exit gradient as per Khosla is fixed. So for single soil, exit gradient is 1 by 4 to 1 by 5. For coarse sand, it is 1 by 5 to 1 by 6. For fine sand, it is 1 by 6 to 1 by 7. As per Khosla, this equation is given as per Khosla. Safe exit gradient as per Khosla. For single, it is 1 by 4 to 1 by 5. For coarse sand, it is 1 by 5 to 1 by 6. And for fine sand, it is 1 by 6 to 1 by 7. So Khosla theory of flow net is made it very clear that the loss of heat doesn't take place uniformly in direct proportion to creep length, as stated by Blake. So it depends the whole geometry of the figure, that is the shape of foundation, depth of impervious boundary, and level of upstream and downstream weight. So when the equipotential line are traced to be closer, the rate of loss of heat will be indefinitely quicker and vice versa. So it can be concluded that safety against piping can be obtained by providing sufficient floor length, as stated by Blake, but can be obtained by keeping the exit gradient well below critical value. So the exit gradient may not be safe if average hydraulic gradient of Blake is L by C. And undermining the floor start from the downstream end of the floor, and if not checked, then travel upstream toward the wear wall. And the undermining start only when the exit gradient is unsafe for the subsoil on which the wear is founded. So it is absolutely necessary to have a reasonably deep vertical cut at the downstream end of the downstream floor to prevent undermining, and the depth of this downstream vertical cutoff is governed by two considerations. So that is the first is the maximum depth of a skirt, and second is the safe exit gradient. Safe exit gradient. So this is the maximum depth of a skirt and safe exit gradient. So for designing a weir, downstream cutoff from the maximum skirt depth consideration is first of all provided and checked for the exit gradient, and if a safe value of exit gradient is not obtained, then the depth of cutoff is increased, and the depth of cutoff is also governed and limited by practical consideration. So as the construction of a very deep cutoff may be difficult to unpracticable at site. So a weir or barrage may fail not only due to seepage, that is the subsurface flow, as stated by Bleak, but it also may be fail due to surface flow. So the surface flow, that is the when flood water flow over the weir crest may cause a scur, dynamic action, and in addition will cause uplift pressure in the jump trough. So if hydraulic jump form at the downstream section. So these uplift pressure must be investigated for various flow conditions, and the maximum uplift due to the dynamic action, that is the surface flow, should then be compared with the maximum uplift under steady seepage, that is for subsurface flow, and the maximum of tools chosen for designing an apron and the floor of the well. So all these modern aspect and other detail about the designing wear on permeable foundation as per Khosla theory have been discussed. So as per Khosla theory differ from Blake's theory in all the above point, but owing to the simplicity, Willig theory is still used for the design of a small work, that is wear and barrage, a minimum practical thickness for the floor, and a deep vertical cutoff at the downstream end. So Khosla method of independent variable for the determination of pressure and exit gradient for seepage below a wear or barrage. Also in Khosla theories, we have to some correction, that is correction for mutual interference of pile, correction for thickness of floors, and correction for slope of floor. So this correction is done by some empirical relation that is given by Khosla as per plate curve. So with the help of Blake's theory and Khosla theory, we can design wear and barrage or a small construction. So write a question. A weir with a vertical drop has the following particular. First is the nature of weight, that is coarse sand with the value of V, that is C equal to 12. Flood discharge, that is 300 cumex. Length of weir 40 meter. Height of weir above low water 2 meter, and height of falling shutter, that is 0.6 meter. Top width of weir 2 meter and bottom width of weir 3.5 meter. So design the length and thickness of apron and draw the cross section of the weir. So this is the question. So given information in this question is that is the a weir with a vertical drop has following particulars. First is the nature of weight. Nature of weight of weir is coarse sand. C equal to 12. Next is the flood discharge. Tens of cumex. Length of weir 40 meter. Height of weir above the low water, that is 2 meter. Height of falling shutter, that is 0.6 meter. Top width of weir 1.5 meter. So total maximum head loss can be calculated, that is HL equal to 2 plus 0.6, that is 2.6 meter. This is the total head loss. The length of total creep length required including creep along cutoff, we can calculate C into HL, where C is given 12 and HL is given 2.6. This is total head loss. So this value equal to 31.2 meter. So the length of downstream floor is given by equation. We can calculate downstream floor, length of downstream floor, that is L2 equal to 2.21 C under root head loss divided by 30. So this value equal to L2 equal to 2.21 C equal to 12, head loss equal to 2.6 divided by 30. This value equal to 18.8 meter, which is approximate Vada meter. And the bottom width of weir is given, that is B equal to 3.5 meter. So for provision of cutoff, let's calculate the discharge, flood discharge which is passing, that is 1.7 H 3 by 2. 1.7 H 3 by 2. So Q equal to Q by L, and this Q equal to 300 by 40, is equal to 7.5, and this value is 7.5 equal to 1.7 into H by 3 by 2. So from this equation we can calculate H. So H is equal to how much? We can solve it. H value. So H equal to 4.41 to the power 2 by 3. So by solving this value, we can find the head over crest weir, that is H equal to 4.41 into 2 by 3, and this value equal to 2.68 meter. This is the head over the crest weir. And upstream HFL, that is by assuming 100 meter bed level and crest level 102 meter, then the total HFL equal to 102 plus 2.68. So this is equal to 104.68 meter. Okay. So according to Lacey theory, we can find R, that is the Lacey-Regime curve depth, equal to 1.35 into Q squared F by 1 by 3, and where F equal to 1 self factor. So R equal to 1.35, Q is 7.5. So how much this value? How much this value? So this value approximate 5.18 meter. So depth of upstream seed pile from below upstream HFL is, we can calculate, that is 1.5 R, and this value equal to 1.5 into 5.18. So this is 7.8 meter. Solving up to this point, now we have to find level of bottom of upstream seed pile. Level of bottom upstream of seed pile. So upstream depth is calculated as 104.68 and upstream HFL 7.8 meter. So how much this value? How much? That is 96.88 meter. So this is the level of bottom of upstream seed pile. So provide a depth of 100 meter, then for upstream cutoff, then the depth of upstream cutoff is 100 minus 96.8. So this value is 3.2 meter. Also we can say 3 meter. This is the depth of upstream cutoff. Okay. Now we have to calculate total creep length that is provided except upstream flow. So total creep length. Total creep length except upstream. So this is the total crumble length. So how much? First is the 2 into 3 plus 3.5 meter plus 12 meter plus then 2 into 3 meter. Okay. So this is total how much? 6 plus 3.5 plus 12 plus 36. So this is total Sorry, this is 6. 12 plus 6. So this is total 27.5 meter. This is the creep length. So to balance length, that is the 31.2 meter, there is a difference. So calculate that difference. So difference is 31.2 minus 27.5, and this value is equal to 3.7 meter. So this, we can say this value is round off, that is the 5 meter, and it is provided as upper stream flow, and hence the total creep length is, if 5 meter is provided for upper stream, so total length is 27.5 plus 5, so this is equal to 32.2 meter. Okay. So total creep length, that is L2 plus L3 equal to 18C under root HL by 13 into Q by 75. So we can find L2 plus L3. So please all put the value of C, HL and Q and find the value of L2 plus L3. Individual value of L2 and L3. This is how much? L2 and L3. So L2 equal to 11.8 meter and L3 equal to 19.8 meter, that is approximate 20. So hence provide for thickness 1 meter downstream loose talus of 20 meter in length. So for downstream length it is 20 meter. So 20 meter can be partly provided as block over inverted filter and partly as launching apron. So the length of upper stream, that is L4, may be kept as equal to half the length of downstream. So that is the 10 meter. Also for design, hydraulic design for where we can permeable foundation may be classified as design for subsurface flow or design for surface flow. For design of where, this point is clear to everyone. L2 and L3, that is the length on clip for downstream side.